Problem number 65 says we have two 50-kilogram weights of a cuckoo clock descend 1.5 meters in a 3-day period. So I have two weights that are 0.5 kilograms each. 0.5 kilograms. And they descend 1.5 meters over a 3-day period. And then it says, what rate was their total potential energy decrease? So really what they wanted to know, what was delta U? And since this is on power, remember that power, when they use the word rate of this, so when we say rate of this, it's a power question. Why? Because power is equal to work over time, but that could also be the change in potential energy over time. Does that make sense? It's a rate of change. In other words, there is a change in potential energy over time. All right, so that's what they want us to calculate, is the power done. So the old clocks, this is how they worked. They used potential energy. They had weights in them, and you would set the weight, and the weight would fall slowly, and as it fell, it would spin a gear, and that gear would spin another gear and spin another gear, and that's literally what made the clocks work. Okay? And then every once in a while, you know, they last 3 days. After 3 days, somebody would have to go in, lift the weights back up, reset the clock at the proper time, and let go, and the gravity just gradually pulled it down. So now to do this problem, we just need to find the potential difference, okay, or the change in potential energy. It's not that hard. It's not as hard as you would think. So along this line, my potential energy, I have two objects that have the same mass, and the potential energy is just this. And technically, I probably should write delta H or delta Y or delta whatever, okay? And then that is going to go over my time. Does that make sense? Now my time, I've got to convert to seconds. Does that make sense? So before I finish that, let's do a couple of things. We said that 3 days can be converted because how many seconds are in 1 day?
8, 6.
It was 86,400, wasn't it? All right, let's do that one first. 3 times 86400. 259,200, right? Is that right?
Yeah.
All right. 259. What was it again?
259, 200.
Like that, right?
Yep.
Because the days cancel with days, and then I get left with an answer in seconds. All right, that's good. And so now I can get to work. So power is work done over time. Work can be the change in potential energy over time. My potential energy is 2 times the mass of both objects times gravity, or the acceleration due to gravity, 9.8, times delta y or delta h, or however you want to, you could also say d for displacement. That was 1.5 meters, okay, all over 25,000 or 259,200 seconds.
For the 0.5, wouldn't that be 1?
Well, we're multiplying it by 2.
Oh, okay.
Yeah, this is how the textbook has it. Yeah, you could just combine them together and call it 1 if you want to, right? And I make an assumption that they both fall at the same time, but sometimes one will fall and the other one pulls up and stuff like this. So we have to make that assumption. All right, so let's plug that in our calculator. So we have 2 times 0.5 times 9.8 times 1.5, 14.7. That's the change in potential energy, joules, divided by 259,200. Oops, got too many 2's there. Is that right? 5.7 times 10 to the negative 5, if I use sig figs and round. So the power then, the average power, or actually the power, not average, the power was equal to 5.7 times 10 to the negative 5 watts.